So far, we've kept caches out of the virtual memory discussions, but now we're going to bring them back into the picture. And it turns out that there are a couple of different ways in which I can integrate caches with virtual memory. And they have a few trade-offs which are interesting, and we will go through them. So the main difference is in terms of how and when the address translation is done using TLB. And so therefore it's worthwhile to understand address translation's importance a little bit. So address translation, like we discussed before, is done for every instruction fetch, meaning for every instruction you need to fetch the instruction from memory, so you need to do the address translation. The instructions that are load or store, you need to do another address translation in its memory stage. So now when to do the address translation? Well, you can do the address translation only after its virtual address has been computed. So for instruction fetch, it's been computed and kept in the program counter, so that's not a big deal. But in the case of a memory access for a load or a store, you can't do the address translation before the execute stage, because that's when the virtual address gets generated. So now after the virtual address has been generated, what do I do with it? Do I go and directly use it? Do I use a virtual address to access the cache, or do I use the physical address to access the cache? And that has an important implication on performance. So now let's take the simpler option first, or more intuitive option, which is the CPU generates the virtual address either in the instruction fetch or the memory stage, doesn't matter. You get the virtual address. Before you access the cache, you do the translation. You look into the TLB, which is effectively a cache for page tables. If it's a hit, you're done. You get the physical address, go access the cache. Well, if it's a miss, you have to go to the main memory, look up the page table, and then do the translation. It will take much longer, but hopefully that doesn't happen very frequently. So, but the main thing to understand here is you take the virtual address, do the address translation, and use the physical address to access the cache. And if it's a cache miss, you go to the main memory and you bring the cache block into the cache. Now here's the important thing. You store that cache block at a place in the cache that is defined by the physical address. So the tag, set index, and the block offset, they're all going to be defined by the physical address. So the set index would be derived from the physical address, the tag would be derived from the physical address, and so the next time when you want to look up the same cache block, you would be able to find them in the right spot. Okay, so now the implication of this design is that for every address that need to be accessed, I need to do the address translation, right? Because I cannot access a cache without the physical address. So first I got to do the address translation. So we'll discuss the trade-offs a bit later, but there's a more efficient way to design this, which is as follows. So instead of addressing the cache using the physical address, I'm going to use the virtual address to address the cache. Well, how is this going to work? Well, it's worthwhile to think about what happens on a cache miss. So let's say the first time I access an address, the cache doesn't have anything, so it's a cache miss. So I do the address translation. So maybe I'm lucky and TLB has an entry and I'm able to do the address translation, or if not, I go to the page table which is located in the main memory and do the address translation. But the important thing is, on a cache miss, I do an address translation and then go and access the memory. I bring back the cache block, store that new cache block in the cache. Let me get the pointer here. So store the new cache block in the cache such that the tag and the set index are derived from the virtual address. So this is the first time when I have accessed this cache block, and I'm going to store it in the cache at a place and tag as defined by the virtual address. So the next time I have to access the same address, I would be able to go and find it using the virtual address. I don't need the physical address to find it because I kept it with its virtual address tag, not the physical address tag. And so this is beautiful because now if there is a cache hit, I don't have to do the address translation at all, because CPU generates the virtual address, you go and access the cache, and you're done. It's only when there is a cache miss you have to go and do the address translation. So as you can imagine, this design can be faster than physically addressed cache. Then what's the problem? Well, we'll see in a moment that it can have some higher complexity when it comes to implementing context switches and ensuring process isolation. So this is another way to visualize the difference between physically addressed cache and virtually addressed cache. So this is an often source of confusion because in both cases we are talking about the same cache, and the only thing that is really different about the two designs is which address you choose. So in the case of physically addressed cache, I'm choosing to derive the tag and the set index from the physical address. Okay, so I take the virtual address, do the translation, get the physical address, and then I can figure out what my tag and set index is. So then I take these two values, go into the cache, look up the right set, and then do the tag comparison. In the case of virtually indexed cache, I don't need to do the address translation because I'm keeping track of everything in terms of the virtual address. So I take the set index and tag from the virtual address, and then I go and access the right set and then get the tags and then do the right comparison. Now maybe you have already observed this, but think about a question here. Would the tags be smaller or bigger for virtually addressed cache? Well, the answer is for a virtually addressed cache, the tags will be bigger because the virtual addresses are going to be bigger than physical addresses. So it's the same data that we are storing, but we have the option to index it with the virtual or physical address, and they have some trade-offs. All right, so let's summarize the two designs before we evaluate the trade-offs. So in the case of physically addressed cache, get the virtual address. In both cases you get the virtual address, but in the case of physically addressed cache, you do the address translation. Here I have simplified it and said, well, look into the TLB and you'll find the virtual address to physical address translation. You take the physical address and then go and access the cache. If it's a cache miss, then go and access the main memory. You already have the physical address, so nothing else to be done between these two operations. The main thing that is different about virtually addressed cache is you do these two steps in the reverse order. So you take the virtual address, you can right away go and access the cache, and only on a cache miss you have to bother about doing the address translation by accessing the TLB. And then you go and access the main memory, because main memory can only be accessed with the physical address, because when we say physical address, we are referring to an address in the main memory. Okay, so now let's take a look at the trade-offs. Like we said, physically addressed cache can be slow because you always need to do the address translation and then get to the cache. And virtually indexed cache, on the other hand, can be faster because you can skip address translation for most of the memory accesses as long as it's a cache hit. The other subtle problem, which is a little bit challenging to understand, and we'll consider an example for it, is that physically addressed caches can be a bit simpler to implement for context switches, and it's more complex for virtually addressed caches. All right, so why are physically addressed caches slower? Well, it's slower because you can access it only after getting the address, and it's also inefficient because you have to do this address translation for all memory accesses. So that's kind of bad from the perspective of power and energy of the processor as well. And virtually addressed caches is very nice because I can skip address translation for as long as I have a cache hit. It's only when I have a cache miss I have to do the address translation. So I save a lot of TLB lookups, and therefore I save a lot of power and energy. What's the downside of virtually addressed cache? Well, we need to think about process isolation and what that means for cache design. Okay, so let me construct a very simple example here. So let's say I have two processes. So like we said before, whenever a process is created, the operating system will go and create a page table for them. So I have a page table for a process A, a page table for process B. Now, let's say I have a virtual address 10, and I can have a virtual address 10 in both processes, because keep in mind that virtual addresses are defined by the ISA. So A and B can both access virtual addresses that range from 0 to 2 to the power of 64 in the case of a 64-bit ISA. Now, the way these two guys, A and B, these two processes are isolated from each other is by the operating system, which ensures that it allocates a page for process A and a different page for process B, even though their virtual addresses are the same. So we talked about this in the case of virtual memory design. So let me call this address to be 100 and this address to be 200. Okay, so same two virtual addresses are mapped to two different physical addresses, and that's exactly what we want, because we don't want Chrome to be accessing Microsoft Windows's data when I'm running both of them simultaneously on my computer. All right, so now why does this matter for a cache design? Now let's think about what happens inside a CPU where there is a cache. I'm going to represent cache as a simple box. So this is my cache. So imagine the operating system has scheduled the process A on the processor CPU. Assume that there is only one processor core and that one is running process A. So obviously process A data will be allocated and stored in the cache. So let's say process A had access to address 10. Now for the moment, let's assume that we are thinking about physically addressed cache. Okay, so I'm going to call it as a PA cache. So in the case of a PA cache, if A accessed address 10, I'm going to store that as 100, right? Because it's physically addressed, and that's how I keep track of it. The tag will be derived from the address 100. Now let's say the process A is context switched out. It runs for a while. After a quantum of time has passed, operating system will come and say, okay, you have had your turn, but now it's B's turn. So now B will have to start executing. Now when B executes, let's say B also wants to access virtual address 10. That's fine. But in this case, B will map to address 200, which is also okay, because I'm using 200 to check the cache, and I will find out that I don't really have the data, so I will be a cache miss, and I go and get the address 200's cache block, and I store it separately in the cache, or maybe it will kick out 100. I don't really care. But the point is, B can recognize that the virtual address 10 is not there in the cache, because it gets translated into the physical address first, and then you go and check the cache. Now, as you could have guessed, this whole process breaks if I use a virtually addressed cache. Now let's go through the same example, but with a virtually addressed cache. So I'm going to make this VA cache. Let's go through this example again. So let's say I have A running first, accesses the address 10. Now this is VA addressed, so therefore I have to keep track of it as in terms of virtual addresses. So when A accesses 10, I bring the cache block, no big deal, it uses it. Now let's say there is a context switch. So when there is a context switch, B comes in, starts executing, and like I said before, B also wants to access the virtual address 10. And in the case of a virtually addressed cache, remember, we don't do the address translation when we access a cache. So you take the address 10, go and check the cache, and what do you find? Well, B finds that the address 10 is actually in the cache. Just a surprise, because this is the first time B is accessing the address 10. It should be a miss, but it's not. It's even worse, because B is now able to access the data that A was operating on. So the entire idea of isolation breaks in the case of virtually addressed cache. Okay, so what's the solution? Well, we got to ensure process isolation. That's not a choice we have. So the only solution then is to say when A was running, it can use the cache as much as it wants, but when the operating system context switches the process out, the virtual cache needs to be invalidated. What does that mean? It means I want to go and mark all the blocks as invalid. Wait a minute, so if I mark them to be invalid, then I will obviously lose the data in the cache. So therefore I need to make sure that whatever data that is there in the cache, if it is dirty, I have to write it back into the main memory, which is okay because it will be stored in a spot that is different from the spot that B is using, which is over here, right? So A will write back the data to main memory at physical address 100, safely storing its virtual address data, right? And then it can basically completely clear the virtual cache so that B can come in and start using it. And B can go and use it for 10, and it will check that, oh, the virtual cache does not have the address 10, which is great, which is what we want. And then it can go and start using the cache and bring the data from physical address 200 into the cache. And then when it gets context switched out, it has to do the same thing, which is evict all its dirty blocks and wipe out the cache state so that the next process can use it. So the big takeaway here is that when there is a context switch, in the case of physically addressed cache, there is nothing to be done. Everything works beautifully. There's no problem. However, if you're using a virtually addressed cache, you have to clear it up because we cannot distinguish between the same address that is generated by two different processes. Two addresses mean different things for two different processes. Two different virtual addresses mean, sorry, the same virtual address means two different things for two different processes. So therefore, on a context switch, you have to clear the cache for virtual caches. And that's a problem because it adds a bit of complexity. And if the context switches are more frequent, so for example, in mobile phones and desktops, when you have a lot of interactive applications, you keep switching between one application and the other, context switches can be frequent. So in that case, you are clearing the cache too often, and that can lead to poor cache miss rate because you'll have more compulsory misses. Because every time you context switch in, you're going to bring all the blocks in, whereas if you did not clear the cache, then you can enjoy a little bit more temporal locality, because if the process B did not kick A's data out, then if A is switched back in, so if I schedule A and then B and then A, now if B did not clear the data, then A would be able to reuse the data that it had in the cache. But in the case of virtually addressed cache, when I context switch to B, everything gets knocked out, and so when A comes in again, there's nothing in it, nothing in the cache for it, so everything has to be populated again. So that's the trade-off. But in most like in supercomputers or even in data centers, when programs run long enough, context switches are fairly infrequent, and so there is not a lot of performance to be gained because you have a physically addressed cache. So what do we really use today in modern process? Well, for level 1 caches, again, if you remember our cache discussion, so CPU has multiple levels of caches. There is a small L1 cache, and then much larger L2, and then even larger L3. All these levels of caches exist because L1 is much faster, L2 is a bit slower, and this one is even slower, 50 cycles or so. And so L1 has to be super fast. So if you want something super fast, you want to do as less work as possible. And so we want to not do the address translation before accessing L1. So therefore L1 caches are typically virtually addressed. However, but L2 and L3 are physically addressed, so that when you context switch processes out, you retain some data, and also you don't have to incur a high latency for a context switch, because writing back the data from L2 and L3 will be much more time consuming, because obviously you have more data in L2 and L3, so it takes more time to clear them up. L1 on the other hand is much smaller, so it's kind of easier to clear them up in a quick time. So I would like to fill in a little bit more details about virtual index cache and physically addressed cache. Just the workflow and the latencies a bit more. There are a couple of points that I didn't make before that I want to make and wrap this up. So in the case of a physically addressed cache, you take the virtual address, you check the TLB. TLBs are really fast, so it takes about a cycle, and then you access the cache. If it's L1, you're talking about one cycle. If it is L2, level 2 cache, it could be tens of cycles. And then if it is a hit, you return the data to the processor. But in case if you couldn't translate using TLB, then you have to look up the memory and do the address translation through the software page table. And that can take hundreds of cycles, because you're looking up the main memory. And so if you find the page to be valid, then again it will be only hundreds of cycles. But if the page is not valid, then you may need to go to the disk, and so then page fault handler needs to be invoked, which would bring the data from the page and update the main memory and the page table and the TLB, and only then you would be able to go and access the cache. It seems like you would spend a lot of time doing this page table lookups and disk lookups, but keep in mind that TLB misses are very rare, very, very rare. So the most common path that you take is TLB access, hit, cache. Most of the time it's a hit, and you return the data. And now if you don't hit in the cache, again you go to main memory, but you already have the physical address, so nothing else to be done. And let's go through the same details for virtually addressed caches. So you get the virtual address cache. The big difference is you don't have to do the address translation. Instead, you directly access the cache, which can be again 1 to tens of cycles depending on the size of the cache. If it's a hit, nothing to be done. Return the data to the processor. Address translation doesn't even come into the picture. But if it is a cache miss, then you have to check the TLB, do the translation. If it's a TLB is a miss, then you have to go to the main memory and then do the page table lookup and then do the translation. And then once you have done the translation, then you go to the main memory and get the data, and then you update the cache. So the other detail that I skipped over before, and it's useful to understand, is in the case of a virtually addressed cache, you have a couple of options as far as when TLB is accessed. So the design that we have been talking about is, well, take the virtual address, access the cache, and do the address translation only on a cache miss. But another option is do the TLB lookup in parallel with the cache lookup. Now, why would that be interesting? Well, if you were to do that, then by the time when you discover that the cache doesn't have the data, meaning it's a cache miss, then you already have the physical address to go and access the main memory. So you kind of shave off a few cycles when you want to go and access the main memory. But the downside of this design, and that's why we didn't talk about it earlier, is you're accessing the TLB all the time, even on a cache hit. And that's not an efficient design, because in modern processors, energy and power are super important. And so if you're going to wastefully access TLB for every memory access when you really don't have to, then that's not a really an efficient design. But that is a design consideration that you may want to consider. Okay, so one final point I want to make is that an operating system provides few more extra features for supporting virtual memory. So in particular, it must be possible only for the operating system to change the contents of the page table, because Remember, page table is how you ensure isolation between the processes. Each process has its own page table, and page table allows you to do the address translation. Now, if user level processes like you and I, who writes a program and runs it on a computer, if we can change the page table, then we would be able to go and access any other program's data, and that violates isolation. So all the changes to these structures can be made only by the operating system. And so in order to make sure that our processes, the programs that you and I write, doesn't modify the page table, operating system has different levels of privilege modes. So it has a kernel level or a supervisor level or a executive level permission mode. So if you're running a particular program under this level of permission, that means a load or a store can access the page table, right? So the certain pages will be marked as kernel mode only pages, and so those kernel mode only pages, meaning belonging to the page tables, can only be accessed and modified only when a process is being run in the kernel mode, and the operating system will let a process to run in the kernel mode only if that process belongs to itself, like page fault handler, for example. And if you and I were to run our own programs on computer, let's say I wrote a program to sort a function and run it on a computer, so that program would run under user level permission, meaning I can do what I want to do with my program, but I won't be able to change the contents of the page table, either mine or other processes. Okay, so for more details on how operating system implements these features, I would encourage you to look up these links, which I have included in the slide. If you want to go deeper into these topics, you should do that. Or if you really want to, if you're really interested in virtual memory and operating system related topics, 482 would be a good choice for an upper level elective.